So negative 1/2. Actually, we'll just factor out negative 1/2 for both of them. So we have the limit as b, bless you, 0 from the left. We plug in b, it gives us b to the negative 2, or 1 over b squared. Minus, if you plug in negative 1, 1 over negative 1 squared, which is just 1. Plus the limit as a approaches 0 from the right. If you plug in 2 squared, you have 2 to the negative 2 power. Well, 2 to the negative 2 is 1 over 4. Minus, if you plug in a, that gives you 1 over a squared. Okay. Which means as this gets closer and closer and closer and closer and closer, you actually end up with 1/2. This becomes negative infinity. So that automatically just throws it all out. Minus 1, the limit of 1 is just 1, so.
Wouldn't that be 0 though, 1 over b squared, since we're going to 0 from the left side?
Nope, because you're getting closer and closer to 0. So if you divide 1 by 0.5 and 0.2, so yeah, so it just gets bigger and bigger. I know it's real easy to mess that one up. Yep, so as 0 gets smaller, gets closer and closer to 0, it's getting smaller and smaller and smaller and smaller. So you have like 1 divided by 0.000000001, so which is really
It's
big.
kind of like 1 divided by 1 over infinity.
Exactly.
Infinity.
Yeah. All right, so you have minus 1 plus limit of 1 over 4 is 1 over 4. Like once you hit that, you don't have to go anymore, but we're just doing it anyway. Plus 1 over 4, and again, as you're approaching here, you're going to go to minus, that just becomes infinity, so it's just minus infinity. So any way it goes, it's just negative infinity. Yes?
I've been confusing myself. So it seems like we're talking about negative infinity. We're not talking about negative. We're talking about a very infinite small number.
No, we're just talking about the patterns getting, the numbers getting smaller and smaller and smaller as you approach, in this case, 0 from the left and the right.
So it's not a negative number though?
No, it's just going in the negative direction.
Gotcha. Okay. Cool.
Mm-hmm. You're welcome. All right. Any other questions? Oh.
Just a question.
Mhm.
If we have an incontinuity at some point n, where like we have one that's some value above or below,
Mm-hmm.
when we approach that value from both sides of the limit, doesn't that technically mean that there is one infinitesimal line of overlap, and thus our integral is incorrect in its assessment for like the area?
Not really. It's because you're not equaling that particular point, but you can get infinitely closer to that point. So let's say if you had x over 1 over x over 5 or something like that, you can get really, really close to 5. You can get 4 and put an infinite number of 0.9s afterward. So you'll never get exactly there, but you're so close, you can pretty much just say, well, we're going to assume this is it, since we're so close. Does that make sense?
Yeah, it does.
Okay. Yes. No. Yeah, I don't know whose hand went up
At
first.
the bottom, you have a negative 1/2 times the whole limit thing, and then at the after the equal sign, you forgot the negative, I think.
Oh, okay.
Wouldn't that make it positive infinity?
Not really.
No.
Nah, not really. Yeah.
Why?
Oh, because negative infinity. Oh, for that one. I'm trying to think, does it? No, it doesn't. Let me see, make sure.
Because that makes it a positive.
Yeah, it does become positive. Yep, you're right. Yeah.
Negative infinity minus negative.
Because you have a negative number times a negative, really big number, it still become positive. Yeah. So it becomes infinity. All right, so any questions on that one? Okay, so we started off with the tough stuff, so now we're going to transition to the little bit not so tough stuff. I didn't want to say easy because that's why I said not so tough. All right, so we're going to start on sequences. Okay. And a sequence is really just a set of numbers on a positive domain. A set of positive integers. Okay. So you have your terms of a sequence. Which is a sub 1, a sub 2, a sub 3, a sub 4. This is really just saying first term, second term, and it keeps on going till you get to some nth term. All right, so let's say, for example, we wanted to list the first 4 terms. Clean that up a little bit. Of, let's say, the sequence a sub n equals 3 plus negative 1 to the power of n.
Those are just basically squiggly lines.
Those are brackets. I think that's just, for me, it's a habit of putting them in. I've been doing it forever, but you don't really need them. All right, so really, a sub 1 is just 3 plus negative 1 to the first power. So it's kind of like functions where you're just replacing the x with whatever's in there. Here you're just replacing the n with whatever sub value you have here. Okay. So 3 times negative 1 to the first power is just negative 1. So you end up with 2. Your second term is just 3 plus negative 1 squared. Okay. Negative 1 squared is just 1, so you end up with 4. Your third term is 3 plus negative 1 cubed. Negative 1 cubed is just negative 1, so we're right back at 2. And the fourth term, 3 plus negative 1 to the fourth. So bring that up a little bit. That's just positive 1, so you end up with 4. So you can kind of see the pattern. It would just go back and forth between 2 and 4. All right, any questions on that one? Okay. So here we have the sequence, and they gave us the a sub n, and we figured out the terms. So now they're going to give us the actual terms, and we have to figure out the a sub n. Where some of them will be easier than others. So, all right, anyone still writing? No. All right, I'll leave that up there for a little bit. All right. Oh, sorry. Oh, still writing. Sorry. Everybody's good. All right. Okay, so let's say, for example, if we wanted to determine the explicit formula for the nth term of the sequence negative 2/3, say 4/5, negative a over 7, say positive 16/9, negative 32/11, and it keeps on going. Okay, where we know that this is our a sub 1. Or first term. Okay. Now with these, there are usually 3 steps that I always follow. The first thing you want to do is you want to notice if the signs alternate. Okay, so you want to notice the alternating signs. And the first one is negative. Okay, so whenever you have alternating signs and the first one is negative, you want to include negative 1 to the power of n. Because when n is equal to 1, it's negative 1. When n is equal to 2, it's positive. When n is equal to 3, it's negative, and it just bounces back and forth. So whenever that first term is negative and it just goes back and forth, you want to include that one. Okay. The second thing you want to do is you want to look at the numerator's pattern. We have 2, 4, 8, 16. Yes.
So that first example we got,
Mm-hmm.
the terms did not have, there were fractions, so are we usually gonna have fractions for these?
Oh yeah, when they're asking you to actually
So always
convert it,
fractions
yep.
pretty much?
Usually it's fractions, not all the time, but
It
in
probably makes it easier then.
yeah.
Because like random numbers are a lot
Yeah.
harder.
So with this one, if you look at your numerator pattern, you don't really have to worry about the signs. We already took care of the alternating signs. So you just have 2, 4, 8, etc. You can actually rewrite them as 2 to the first, 2 squared, 2/3, and it keeps on going. So since you can kind of see the pattern there, you include 2 to the nth power. Okay. So your third step is you want to look for your denominator pattern. Okay, so you have 3, 5, 7, 9, pretty much just odd numbers. So whenever you have odd numbers, if you had even numbers, you could just make it 2 times n. If you have odd numbers, you can make that 2 times n plus 1. Okay, so you have, oh, actually in this case, it would be 2 times n minus 1. Because you're starting at 1. Nope, plus 1 because it's 3. I was looking up there. Sorry about that. Yep, so it will be 3. So it's plus 1. All right, so that means you would include 2n plus 1. Okay, so you have your alternating signs taken care of, you have your numerator taken care of, and you have your denominator taken care of.
Why does it have to be 2n plus 1? Why couldn't it be n plus 2?
What do you mean n plus 2?
Instead of 2n plus 1.
You get the second denominator with
Oh,
a
yeah.
4.
Yep, so if you have, I mean, that would work for the first one, but it has to work for all of them afterwards. So if n is equal to 1, and 2 times 1 plus 1 is 3. If n is equal to 2, 4 plus 1 is 5. Because n is equal to 3, and it just keeps going for each term.
Oh,
Yep.
I see.
All right, so just like before, this is your first, second, third, all those terms. So that's where the n's come in. All right, so we have our alternating signs. So we include, you can put it up front or up top, doesn't really matter. So you have negative 1 to the nth power. In your numerator pattern, you know that's 2 to the nth power. Over your denominator pattern, which is 2n plus 1. And that would be your answer. Yes.
So, I'm sure there's a lot of different formulas that can result in that.
Mhm.
How specifically, how do we, like, do we care that there's multiple, or that's just like an outlet? Like, is there
Oh, no, this one, yeah,
like
this,
an outline?
yeah, for this is kind of just like an outline for it. So this is pretty much just an approach.
Okay.
Because they get, some of them can get a little trickier than this one.
I'm sure.
All right, any questions on this one? All right. So let's, oh, we're still writing. Yeah, all right.
If a sequence of functions whose domain is a set of positive integers, why were there negatives?
You mean if all,
It was the definition of sequence.
Oh,
that
positive
used
integers?
Positive integers.
Oh,
And
yeah.
The second example used negative numbers. Well, I guess they used
Nope.
negative
You
fractions.
did say positive integers.
You told positive integers.
oh no, the a sub, the 1, 2, 3, and 4 for a sub 1 and 2, those are positive.
Oh, okay,
Yeah.
I see.
Yeah.
So
Yep.
that's just referring to you're not gonna have a negative one.
Exactly.
Negative two, okay.
Yeah, that's it.
Is there a math that goes that way?
Yeah, they do, just not here, but yeah,
Right.
it
Proper
does.
sequences.
Oh, wrong one. It's the same one, yep, same one, so it goes over here. All right, so let's say, for example, if you want to give the explicit formula for the nth term for the sequence, say 8 over 9, negative 64 over 17, 512 over 25, negative 4,096 over 33, 32,768 over 41, and it keeps on going and going and going. And we know this is our a sub 1. right, so just like before, you want to notice the alternating signs. It's going from negative, positive, negative, positive, negative. But this time, the second one is negative. Okay, so whenever the second one is negative, you want to include negative 1 to the power of n plus 1. Because if n is equal to 1, that becomes negative 1 squared, so that's positive, then negative, and positive, and negative, and back and forth. Okay. Now the second, you want to look at your numerator pattern again. Okay. Where you have 8, 64, 512, 4096, and et cetera, and so on. Now the first two should give you an idea of where to start. Yep, because that's 8 to the first, 8 squared. Then if you test that one, you'll see that's 8 to the third, and it keeps on going. So the other numbers kind of scare you, but if you look at the first two, they usually can give you an idea of where to start. Doesn't always work, but gives you an idea. Okay, so now that means we're going to include 8 to the nth power. Okay. Now the third step, you want to look at the denominator pattern. Where you have 9, 17, 25, 33, 41, et cetera, and so on. Okay. Now, just from looking at it, nothing jumps out. So a lot of time, if nothing jumps out, what usually helps is if you look at the distance between all of them. You can usually see a pattern there. So the distance between 9 and 17 is 8. 17 and 25 is 8. 25 and 33 is 8. 33 and 41 is 8. So they all have a distance of 8. So you know it's going to be an 8 times n somewhere in there. But if you look at it, 8 times 1 is 8, which is, if you add 1 here, would give you 9. 8 times 2 is 16. If you add 1, 17. 8 times 3 is 24. If you add 1, 25. So you can kind of pick it up there. So if you look at the distance between the two, it gives you something to start with. Because looking at that, it's no way to just look at it and go, oh, okay, and plug it in. Okay, so you want to include 8 to the n plus 1. Well, 8 times n plus 1. Okay, so we have our alternating signs, we have our numerator, and we have our denominator. So you have your negative 1 to the n plus 1 times 8 to the nth power over 8 times n plus 1, which would be our answer. All right. Any questions on that one? All right, I'll leave that up for a few seconds. Or is everyone done? Okay. Oh, I'll leave that up. All right. Okay, so now these are recursively defined sequences. That means each sequence depends on the term before it. Okay, so let's say, for example, find the explicit formula for the sequence where we know that the first term is equal to 6, and every term after that is equal to 5 times the previous term for every term bigger than 2. And actually, these, in my opinion, are a little bit easier than the other ones. Because the first thing you want to do is write out a few terms. Write out a few terms. Oh, clean that up some. And look for the pattern. Okay, so we know that the first term is 6. Okay. Our second term is equal to 5 times, since our n is equal to 2, bless you, and I'll put n equals 2 here. 5 times a to the 2 minus 1, so that's 5 times a sub 1. Since our a sub 1 is 6, a sub 2 is equal to 5 times 6. Now we go to our third term. That's equal to 5 times 3 minus 1 is 2. Okay, so we know that our A3 is equal to 5 times 5 times 6. Which you can make it 6 times 5 squared, or 5 squared times 6, doesn't matter. Okay, now n equals 4. That's 5 times the third term. Which means that our fourth term is equal to 5 times our third term, which is 6 times 5 squared. Which is 6 times 5 to the third. So you can kind of see where that pattern's going. So it's safe to assume that our nth term would equal 6 times 5. Now if you notice here, the fourth term has a third power. The third term has a second power. The second term has a first power. So that would be 5 to the n minus 1. All right, so any questions on that one? All right. Leave that up for a few seconds. Okay. Okay, do say, for example, if we wanted to give an explicit formula for the nth term.